The 3 tripwires, signals of destabilization. Start with what you can see from space. Today, not in a simulation. In a world map of warming seas, there's a stubborn blue bruise south of Greenland, the cold blob. It shows up in NOAA, Hadley, ERA datasets. It shows up in the latest anomaly maps you can pull up on your phone right now. Everywhere else runs warmer over the last century, but that patch cools relative to its surroundings. It's not magic, it's a missing delivery. Less warm water is reaching the surface there. That's the first tripwire, a fingerprint. Many studies associate with a weakening AMOC, the same dipole pattern that pairs subpolar cooling with a warmer stripe along the shifted Gulf Stream. You don't need to trust any one model to notice the anomaly. It's lodged in observation maps year after year, and in recent winters it has intensified against record-breaking global ocean heat. Make it concrete. Airlines reroute around turbulence bands that set up along sharper temperature contrasts near that patch. Fishermen out of Newfoundland talk about green water lines where the temperature drops and fog clings a day too long. Weather desks in Europe watch that blue oval like a pressure cooker valve because it sets the tone for downstream blocking. This isn't a contour plot curiosity. It's a live feature nudging the weather you step into. Why does that matter to people? Because that patch isn't just a color on a chart. It's the sign of less ocean heat released into the atmosphere where European weather is forged. Shift that background field and you tug on pressure patterns, storm paths, and the seasons people rely on. That cold patch is a quiet, persistent note played under winter forecasts, and it keeps getting louder. Now pan from satellites to sea level along the U.S. East Coast. Again now. Tide gauges from Norfolk to New York tell a story of water creeping higher, faster than global averages at times. Nuisance floods have multiplied within a single career for harbor masters. Part of that is ice melt and thermal expansion, but part of it is dynamic. When the deep southbound limb of the AMOC slackens, the north-south pressure gradient across the Atlantic eases, and water stacks up against the coast. Think of it as a barometer for the Atlantic's muscle. That's Tripwire 2's cousin, because the same physics show up in another metric, the sea surface height and density gradient across the Gulf Stream. Oceanographers watch the tilt of the sea surface across the current and the shear of velocity beneath. When the Gulf Stream weakens, the slope flattens a touch and coastal sea level nudges up. Long records stitched from altimetry, tide gauges, and hydrography suggest episodes of weakening over recent decades, consistent with a gentler AMOC. Meanwhile, moorings strung across the Atlantic at 26.5 degrees north, the Rapid Array, have tracked notable year-to-year swings and a long-term decline from the early 2000s baseline. It's not a straight line, and it's not decades long yet, but paired with indirect proxies, it adds weight. And it's happening in the only sustained direct observing line we have. About those proxies. We can't put a flow meter on the entire overturning for the last 100 years, so scientists use fingerprints that physics predicts. The cold blob is one, the gradient across the current is another. There are also density reconstructions from the subpolar North Atlantic, sediment records that reflect past deep current strength, and the growth bands of corals that preserve changes in water mass properties. Different archives, different methods, same direction. The AMOC today is likely weaker than at any point in centuries, perhaps a millennium. Each line has caveats. Together, they form a picture you can't wave away with a single counterexample. Now for the third tripwire, the one that hides in noise but is flashing in real data sets. As complex systems approach a tipping point, they tend to recover more slowly from small nudges. Statistically, that shows up as critical slowing down, rising autocorrelation, and rising variance in time series that track the system's state. In plain terms, the system's wobbles last longer and grow larger because it's losing its restoring force. Researchers have applied these early warning indicators to AMOC-sensitive fingerprints, including reconstructed temperature and salinity contrasts across the Atlantic. They report trends in those indicators consistent with decreased resilience, and some studies go further, estimating a mid-century window for a tipping event under current forcing. That's a bold claim, so let's be clear about what's measured and what's inferred. We do not have a century-long direct measurement of the AMOC's full strength. Moorings like rapid date to the 2000s. The Gulf Stream itself is just one part of the overturning, not the whole. Sea surface temperatures can be pushed around by winds and aerosols as well as currents. Early warning statistics can be fooled by the choice of window or by unrelated variability. Those are real limitations. But here's why the inference remains strong and urgent. The cold blob persists across methods and datasets and lines up with known dynamics of reduced heat import. The sea level and gradient signals have the right sign and appear alongside independent evidence of subpolar freshening and increased stratification where deep water forms. The moorings see variability that matches wind-driven changes, but also a background easing. Paleoclimate analogs show the AMOC has two distinct modes and can jump. And the early warning metrics aren't alone. A newer, physics-based indicator looks at the freshwater transport at the southern boundary of the Atlantic. In models that actually tip, that transport passes a minimum on the way to collapse. Reanalyses hint the real ocean may be moving in that direction, and that's a real-time budget, not a vibe. Bring those threads together and you get 3 alarms you can watch today. A visible fingerprint on the sea surface, a mechanical slackening registered in gradients and coastal water levels, and a statistical heartbeat that's slowing. Add cross-checks, sediment drifts that thin when deep currents weaken, coral geochemistry that records water mass shifts, isotope patterns that track past overturning changes. None of these alone proves a countdown. Together, they say the system is losing stability.
Now, what nobody knew in the 1990s was how fast a modern shove could matter. Aerosols, for example, once masked warming over the North Atlantic and may have muddied earlier signals. As those aerosols declined, greenhouse forcing stood out, and the structure of the ocean began to wear its stress more plainly. Freshwater input ramped, stratification grew. The tripwires started to glow, and they haven't dimmed. So the question becomes, if these alarms are real, where does the road bend? Past the threshold, the approach can take decades. But the transition itself, the flip, can compress into months or a few years. We're not waiting for future instruments or future models to tell us whether to care. The instruments we have already show direction. We need to talk about how slow pressure yields sudden change, why the path back is harder, and what that means for lives arranged around assumptions of gradual shifts. That's where we're heading next. Tipping points. How a gradual push becomes a sudden flip. Think of the AMOC as a ball resting in a shallow hollow on a hillside, but put your hands on it. Feel how it settles after a nudge because the hollow cups it. Now imagine a slow, invisible jack beneath the hollow. That jack is fresh water. Each year it lifts a millimeter. You don't notice at first. The ball still rolls back after pushes. The lip still holds. Then one winter, the jack is lifted enough that the lip isn't a lip, it's a line. A storm pattern tilts the board. Deep convection sputters in the key basins, and the ball kisses the edge. There's a split second when it could stay, then it tips. Gravity takes the rest. It doesn't clatter back into the old cradle, it drops into the next one down, and your hands can't stop it. Here's the physics behind that picture. Freshening reduces surface density, so winter cooling has to work harder to make water heavy enough to sink. While sinking weakens, less cold water drains from the surface, and more heat stays trapped below the fresh cap. That subsurface warming further stabilizes the water column. Warm water under cold is a loaded spring, reducing mixing and sinking even more. Meanwhile, with less heat delivered north, the subpolar surface cools relative to the subtropics, sharpening the temperature gradient that drives winds. Those winds can spin the subpolar gyre tighter, corralling even more fresh water over the sinking zones. That's a feedback stack. Each notch of weakening sets up the next, so the next nudge bites harder. Multiple stable states fall out of those feedbacks. One mode has strong overturning, salty subpolar seas, and robust winter convection punching to depth. Another has a much weaker or collapsed overturning, fresher subpolar surfaces, and shallow or intermittent convection. The same CO2 level can support either state depending on how the system got there. That's hysteresis in plain language. Path matters. Push the system over the rim with enough fresh water and it snaps to the weak mode. Ease off later and it doesn't snap back. You have to back away far beyond the original line, reduce the forcing well below the point where it flipped to climb out of the lower hollow. That's not stubbornness, it's built into the physics. Models test this with hosing experiments, adding fresh water to the North Atlantic at controlled rates. Many find clear thresholds, push beyond them, and the AMOC plunges to a low state. Stop the hose and it stays down. Only after removing far more fresh water than you added, or cooling the climate enough to resharpen density contrasts, does it climb back. The exact liter per second at which models tip varies, but the geometry of the response,
two basins of attraction with a ridge between them, keep showing up. In higher resolution setups that better capture narrow sinks and swirling eddies, the threshold shifts, but the basic landscape remains. The ridge is real, where it lies is the detail. Time behaves oddly around a tipping point. The approach can be slow because the system absorbs stress. You get years when deep convection returns, headlines calm, and it seems like a false alarm. But the restoring force is fading. Recovery from each perturbation grows more sluggish. Then a sequence of winters lines up. Fresh cap thick, gyre tight, storms less able to crack the lid, and the remaining pathway for sinking constricts. The change in the overturning strength during the actual transition can be steep, months to a couple of years in models that resolve key processes. Recovery, by contrast, is glacial, because the weak state reorganizes the whole basin and the feedbacks that hold it. Once you're in the lower hollow, the walls are higher and slick with feedbacks. This is why we'll adapt gradually as a risky bet. Many impacts of climate change scale with temperature in a way that planners, at least in theory, can track. A tipping circulation doesn't. It rearranges baselines. Europe's energy system, sized for milder winters, suddenly face sustained cold loads and new storm patterns. Rain belts shift, and farmers who spent a decade adjusting to earlier springs confront colder, wetter ones. Fisheries that migrated slowly north don't just keep moving. The plankton communities beneath them reorganize as nutrient pathways change. Insurance models built on last century's statistics break because their hazard maps assumed continuity. One more wrinkle: partial collapses. The AMOC isn't a single pipe. It's a network of formation sites and pathways. You can lose deep convection in the Labrador Sea, while the Nordic seas carry more weight, or vice versa, for a while. That creates regional expressions of the flip. The cold blob can intensify even as some parts of the overturning limp along, masking the severity if you only watch one index. But the integrated heat and salt budget still moves toward the weaker mode if freshwater keeps rising. Why does this matter now? Because early warning.
Signals suggest the restoring force is already dimming. Rising autocorrelation and variance in AMOC-sensitive fingerprints tell us the ball sits closer to the rim, close enough that a few unlucky winters could do the tipping. A newer, physics-based indicator, the minimum in AMOC-induced freshwater export at the southern Atlantic, adds a concrete gauge. In models that tip, that export weakens towards zero, then reverses as the circulation collapses. Reanalysis hints we're trending that way. Add observed subpolar freshening, thicker stratification, and an entrenched cold blob, and the ingredients for nonlinearity stack up. This isn't a centuries-away curiosity, it's within our lifetime's planning horizon. So the story arc shifts. We're not just tracking a slow decline we can hedge around. We're walking along a ridge, already leaning. The view may not change much for a while. Then you take one more step, and the ground drops away. The path back isn't the same trail. It's longer, steeper, and only available if the overall heat load falls well below the point where we slipped. Every ton of greenhouse gases, every gigaton of melt, leans that ridge a little further. Every cut buys time to stay on top. That's the choice set, and the clock runs on seasons, not centuries. 50-50, Europe's winter shock, and the jet stream twist. When the ocean stops handing Europe its quiet ration of heat, the atmosphere has to do the work. And it doesn't do it gently. Over the subpolar Atlantic, a weakened AMOC cools the surface relative to the subtropics. That sharpens the horizontal temperature gradient the jet stream feeds on. In winter, the jet can strengthen and shift, steering deeper, faster-moving storm systems across the North Atlantic. At the same time, blocking highs can lock in longer cold spells over Western Europe, because the background ocean warmth isn't there to blunt them. That's how a warming planet still deals out week-long freezes to a city like Dublin, radiators on full blast while global ocean heat hits records. Stakes first, what you actually feel. The cold arrives and stays. Your breath fogs in the hallway because the staircase bleeds heat. Condensation beads on inside window panes and turns to rime overnight. School texts say closed. Your power app pings with surge pricing at 7 a.m. and 7 p.m. You shuffle sockets to keep the kettle and space heater from tripping a breaker. The boiler groans. Gas storage that used to cover February now runs thin in January. Grids built for occasional snaps face sustained stress. Operators issue conserve now notices, voltage dips. Some neighborhoods roll through 1-hour outages at breakfast and dinner to keep the system up.
Wind farms ride turbulent jets and then, under a blocking high, go still for 4 days. Interconnectors hum until ice accretes on lines, and crews crawl out at 3 a.m. with de-icers and headlamps. Transport doesn't keep up. Ice on runways in places that rarely needed de-icing crews becomes routine, with queues of flights waiting on glycol they didn't order enough of. Trains slow as rails shrink and points freeze. Leaf fall timetables look generous compared to blocked week timetables. Roads heave and crack under repeated freeze, thaw. Gritters run out of salt by Thursday. Bus doors freeze in their tracks. For families, it's the budget pivot. Heating over food or food over rent when the cold stretches a week beyond what they counted on. You move everyone into one room at night to keep pipes from freezing. You learn which cupboards hide external walls because the milk goes cold in them. Here's what actually plays out in the air, minus the jargon. Think of the jet stream as a fast river of air that likes temperature contrasts. The cold blob south of Greenland cools the air above it, steepening that contrast with the warmer subtropics. The river speeds up and snakes more. Sometimes it kinks so deeply that a high-pressure dome parks over Europe, a block. Under a block, the storm track detours north or south, and the same cold, dry continental air just sits. No new air mass comes to flush it out, so overnight lows ratchet down day after day. When storms do break through on the block's edge, they hit sharper pressure gradients and carry more punch, stronger winds between the lows and highs. There's a paradox to precipitation you'll notice on your street. A strengthened jet can fling more frequent, intense winter storms toward the British Isles and the North Sea corridor. Yet less ocean heat under the storm track can reduce the moisture feed near Europe's coast, bringing more of the water out upstream. So some regions see fewer, drier weeks overall. Then the pattern flips for 48 hours and funnels moist air from the south, and you get a burst of heavy snow or freezing rain that snaps branches and downing lines. That's whiplash. 2 quiet, biting weeks punctuated by a storm that glazes every pavement and shuts the ring road. Meanwhile, the ocean surface answers back with reduced
Heat import. Parts of the subpolar North Atlantic can favor winter sea ice regrowth on the margins after a collapse, especially in sectors near the Labrador and Nordic seas. That doesn't mean Arctic pack ice roars back basin-wide, but regionally, new ice edges shift storm formation and wave fields. Coastal waters around Iceland and Greenland see rougher seas under a colder cap. North Sea waters may develop stronger stratification episodes under calmer spells, then overturn abruptly in storms, venting heat in bursts instead of a steady bleed. Fuel for sudden squalls that catch ferries between harbors. Impact isn't just meteorological. A colder, stormier North Atlantic disrupts shipping lanes with more frequent, severe extratropical cyclones. Ferries cancel, ports stack containers, offshore maintenance windows shrink for energy infrastructure. Metro systems struggle with ice blown into open cuts. Points heaters fail in strings. Insurance models that price winters as windy and wet but moderate begin to price them as windy and freezing with clustered loss events. For cities, freezing fog and black ice become regular line items. Ambulance calls spike for falls and hypothermia. For rural regions, frozen topsoil delays spring planting. Then thaw and rain combine to waterlog fields, compressing the farm calendar into a narrow, riskier window. A micro-story brings this home. In County Meath, Maeve's neighbor Liam runs a small dairy. He used to schedule calving to beat the worst of February and hit the early March grass surge. Now the first March week sits under a blocking high. Nighttime lows drop below -10 for 5 straight days. The pasture crusts like glass. Pipes freeze in the milking shed despite heat tape. The smart meter shows red for hours each morning. The co-op texts about conserving power. He burns through his hay reserve a month early and phones a cousin 2 counties away for feed at prices he swore he'd never pay. On day 6, the wind flips. A coastal low barrels in, sleet ricocheting off galvanized roofs, roads close. The line to the creamery goes down. He watches the forecast on a cracked phone screen and starts calculating losses. One more knock-on, energy systems. Europe's transition bet heavily on wind and interconnectors that smooth out variability across regions. In a colder, more blocked winter regime, wind output can be feast or famine. Long, still frigid spells under high pressure. Then roaring days when turbines must feather in gales. Power markets spike just as heating demand peaks. Gas peakers run hard if they exist.
If not, rolling shortages hit at breakfast time, crews de-ice transmission lines by helicopter, substations trip on ice and salt fog. Planners tasked with resilience suddenly need cold, hardy transformers, more storage measured in days, and pricing that doesn't crush households when the jet stream decides to camp. Through all of this, remember the scale. We're not talking about every winter turning into 1963. We're talking about shifting odds and more clustering of extremes. The background state tilts toward colder European winters compared to a world with a strong AMOC, even as global mean temperature climbs. That's the paradox you'll hear at the pub. Record global heat, record local cold snaps. It shows up in the data and in high-resolution simulations that collapse the overturning. Stronger westerlies over the North Atlantic, deeper storms, and less winter precipitation in parts of Europe despite louder weather. The fingerprints are consistent with what Maeve heard on the radio. Unusual, then record-breaking, then simply the forecast. As you can see, rain belts on the move, monsoons, drought, and flood. While Liam counts bales in County Meath, the tropics adjust their aim. Shift the Atlantic's heat, and you tug the planet's main rain belt, the ITC, off its usual track. With a weakened AMOC, the North Atlantic cools relative to the south. The ITC follows the warmth, edging southward. Think of it like a fire hose drifting a few streets over. Every house that counted on that water suddenly runs dry, while the next neighborhood floods. It sounds abstract until you stand in a village that counts weeks to the first planting rain, and those weeks stretch stakes first. When the rain belt moves, food security moves with it. Planting windows shrink or arrive late. Seeds rot in dust or drown in a weekend. Reservoirs miss refill seasons, and ration cards return. Cities built around predictable downpours see gutters run dry for a month and then suddenly overflow in an afternoon. For people, it's harvest yields, water taps, and flood lines etched higher on living room walls. It's food prices on a chalkboard doubling by Thursday. Here's what unfolds. Over the tropical Atlantic, a south-shifted ITC boosts convection closer to the equator and into the southern hemisphere. West Africa feels that as a rearranged monsoon. The Sahel's northern edge retreats, the core rains concentrate farther
to south, and the season's rhythm turns erratic. Some years bring a shorter, sharper burst. Others deliver a late, weak onset that leaves seedlings stranded in hot dust. Farmers who used to plant on the third storm now wait for a fourth that comes 2 weeks late, if at all. Wells drop by a hand's length. Pasture browns early. Herders sell animals cheap, and meat prices still climb because grain to feed the rest is scarce. Meanwhile, across the ocean, the Amazon's water budget changes. With the ITC displaced and the Atlantic temperature gradient altered, moisture transport from the ocean into the basin weakens in parts of the year. The dry season stretches in the western and northern Amazon. Streams shrink to strings of warm pools. Fish die-offs dot banks that smelled of rain for generations. Trees close stomata to save water, dropping leaves early. Lightning finds drier crowns and fires run longer. In the south, some models find wetter seasons after an overturning collapse, but timing matters as much as totals. A late season dump can still be a net ecological stress if early dry months scorch. Saplings fail and canopy gaps widen. The forest's resilience, rooted in deep groundwater and cloud feedbacks, faces a new pattern it didn't evolve for, with knock-ons for regional rainfall recycling that cities depend on. South Asia isn't spared. The South Asian monsoon feeds on land, ocean contrasts, and upstream moisture pathways that feel the Atlantic's push. A weaker AMOC tends to reduce the northern tropics' heat draw, weakening the large-scale thermal contrast that powers the monsoon circulation. On the ground, that can mean a delayed onset, a sputtering first phase, and long breaks between active spells. Rice paddies crack in June, then floods slam them in August when stalled lows dump a month's rain in 3 days. The crop calendar becomes a gamble. Transplant earlier and risk drought, wait longer and risk flood. Groundwater pumps hum for hours and pull up sand. Diesel bills eat margins. Urban India and Pakistan watch reservoirs skate toward dead storage, and then jump back with a single storm that also floods, underpasses, clinics, and shops. Unknown to them, across the Pacific, the Caribbean, and Central America ride the same seesaw.
With an altered Atlantic gradient, tropical cyclone genesis zones and easterly waves change their behavior. Fewer but slower storms can sit over mountain valleys, wringing out catastrophic totals. The rainy season feels like a string of near misses, then a bullseye. Landslides take the same hillside twice in 5 years. Coffee growers lose blossoms to drought, then cherries to rot. Concrete examples are everywhere when the hose drifts. West Africa, millet sown on the second good rain fails twice. Goats are sold at half price. School lunch programs switch to 1 meal a day. Market rice jumps 20% in a week after an export ban abroad. South Asia, a 2-week break in July kills transplanted paddy. Then a cloudburst drowns storage pits. Onions and cooking oil spike. Ration queues lengthen. Migrant labor flows to cities that are already rationing water. The Amazon, smoke from a longer dry season closes airports. Barge traffic slows on shrunken rivers, so soy and fuel arrive late and cost more. Towns run generators all night. Clinics treat respiratory cases in corridors. Back to West Africa for a micro story. In northern Ghana, Amina's cooperative keeps seed in a locked trunk. Their rule was simple: plant after the first 2 solid rains. This year, the first arrives in late May. The second doesn't come. Daytime highs beat the seedlings down. They replant in mid-June after a dusty squall. Then the sky opens, 4 days of sheets. The new channels they dug last year aren't enough. Water jumps the bank, eats a path through the maize rows, and fills the well with brown. The co-op's grain bank opens early and empties early. The price board in town changes twice a day. They salvage what they can and spend the evening tallying debt. In the U.S. East Coast corridor, the knock-on isn't a monsoon, but storm track and moisture feed. A different jet configuration funnels slow-moving nor'easters that stall over coastal plains. Warmer air holds more moisture, and with altered steering currents, those systems dump longer. River basins already swollen by sea level rise see compound events. Surge at the mouth, rain inland, and tides that won't let the water out. The map of once-in-a-100-year floods redraws itself every few winters. Meanwhile, northeast Brazil and parts of West Africa live with whiplash. Drought that primes soils to shed water, followed by convective bursts that do exactly that. Urban drainage, designed for old intensities, caves under new peaks. Rural roads vanish into gullies. Insurance doesn't cover smallholders. Relief arrives late. People move to towns on rumors of steadier work, and towns strain underwater rationing that used to be a summertime story and is now a March to October. Reality. Food staples sit in the crosshairs. Wheat belts in Europe face colder, wetter springs. Rice in South Asia sees erratic transplanting windows. Maize in the Sahel shifts south with the rains, crossing borders and customs that don't move as easily. Global markets feel it. Exporters pause shipments after a bad monsoon. Importers scramble, and price spikes ripple through places that never heard the acronym AMOC. A bag of rice in Accra, a loaf in London, both carry the cost of a rain belt nudged a few hundred kilometers. Food inflation becomes a background noise in headlines. For households, it's fewer proteins and thinner porridge. So while Maeve scrapes ice from a doorstep in Ireland, Amina watches clouds misfire over a field in Tamale. Different latitudes, same cause. A circulation you can't see from shore shifted the line where air rises, and everywhere that depended on that line learned how fragile normal can be. The ITC isn't a trivia term. It's the switch that decides whether seed sprouts or spoils, whether a reservoir fills or a tap hisses, whether the market board chalks the old price or wipes it clean by noon.